is only my second Zoom talk ever, so please bear with me, everyone. I'll try to keep an eye on the chat, but just feel free to yell, or I guess you don't have to yell, if there's something that you don't understand and ask a question, and that's totally fine. So I'll be talking about an epiperimetric approach to isolated singularities. This work is a little bit older, but I guess it's nice to talk about older work. You have a better perspective. And it just came out this year in the journal, so I guess it's nice to revisit it too. All of this is joint with Luca, who's at UCSD, and Bojo, who just moved to Pisa. Great. Okay, so let's start with what the point of this talk is. That way you can listen to this slide, and if you don't like what I'm talking about, you can go off and make a sandwich or do anything else you do on Zoom when your video is off. So let me move this over here so I can see what's going on. So we'll be talking about minimizers to variational problems, and it's a well-known phenomenon that if you minimize from sort of functional, you're going to have a minimizer which is smooth most of the time, but there'll be a set of sort of exceptional points. And around these points, we still want to understand what the behavior of the minimizer is. You know, we care about every single point here for a number of different reasons, depending on the application. And so it's not enough for us to just throw out the sort of small bad set. So one sort of standard technique is to zoom in at these points, and in a sort of weak sequential limit, we'll get a globally defined minimizer to our problem. But the problem with these sort of compactness type results is that the limit we get could depend on the sequence of scales that we zoom in on. This problem is known as the uniqueness of blowups problem. So what we want to understand is whether or not this limit depends on the sequence of scales that we're zooming in on. And the main sort of result is that we show that there are uniqueness of blowups for isolated singularities for these Alt-Caffarelli type functionals. And I'll give a little bit more information about what these functionals are and why you should care. And the key tool is something which is called an epiperimetric inequality, which is interesting because it uses the variational structure as opposed to the associated Euler-Lagrange equation. So maybe this is sort of what you should take home from this talk if you take home anything. Okay, so let's talk about this functional. The functional, which I define here restricted to a ball, Bxr, is the Dirichlet energy plus this other weird term which I have in red, which is the measure of the positivity set of the function. And we say that something is a minimizer if it's less than anything else which shares its same boundary values on the ball. And we want this to be true for every ball inside of our set omega. Usually we don't care so much about what omega looks like or about balls which sort of touch the boundary of omega. This is going to be about information sort of strictly interior to some domain. And this is just a fancy way of saying that U and V share values on the boundary of the ball, right? Because a priori, U and V are just W12 functions, so maybe you don't want to prescribe them on a, well, yeah, I guess you could prescribe them on a thin set anyway. So I don't know. This is just a fancy way that people talk about these things. Great. This function isn't differentiable, and we'll talk more about that later. But you can still, if you're very careful, take some derivatives of it and find out that critical points satisfy the following coupled systems of equations, right? Which is that critical points are harmonic where they're positive, and their derivatives are equal to 1 on the boundary of their positivity set. I put these little scare quotes because unless this set is smooth, it's a little bit unclear what one means by even taking a derivative at points along this boundary. But you should think of this condition as happening in a weak sense, if you'd like. Okay, so now let me give you some examples of critical points. So the most standard critical point, or maybe the most important one, is xn plus, right? So you can see that it's harmonic where it's positive, and that its derivative is equal exactly to 1 on the boundary of its positivity set, which is just Rn minus 1, right? So Rn minus 1 equals the boundary of the positivity set. But another thing that you could look at is something like the absolute value of xn, which still satisfies this condition. But here you have to be a little bit careful. This is not going to be a minimizer. It's just going to be a critical point. And that sort of makes sense, right? It doesn't make sense for a minimizer to go to 0 if it has a positive Dirichlet conditions on the ball. Then you should just fill it in with the harmonic function with these Dirichlet conditions. Okay, great. But these are not the only critical points. There are other critical points in the plane which have more complicated free boundaries. So here, you should think of these as sort of being like a hairpin. This looks a little bit like the catenoid in a plane. And then it's a little bit hard to write the explicit formula, but there is a function which you can see using conformal mapping, which is harmonic inside of this area, and whose normal derivative is identically equal to 1 on its free boundary here. So, okay, here are just some critical points. This first one is sort of the most important. And these other two examples are just to show you that things can be a little bit more complicated than you might imagine, right? These things certainly don't look like just harmonic functions because of this weighting up here. Great. Cool. So before we go any further, if you haven't spent a lot of time thinking about this functional, you might ask the question, why this functional? It's a great question. So let me try to justify it a little bit. So this functional has lots of connections. It was first introduced to study jet cavitation, and people still encounter this functional when looking at certain models for water waves. More recently, it's been used a lot to understand shape optimization. So, what is the way to split a domain into 5 separate pieces such that the sum of the first Dirichlet eigenvalues of the first 5 of these 5 pieces is as small as possible. This also has connections to problems involving harmonic measure and lots of other different problems. So it's a pretty well-studied functional. This is also a prototypical free boundary problem. The behavior of this set sort of dictates the behavior of the solution, and that makes sense, right? We remember that U is harmonic when it's positive, and U is equal to 1 on the boundary of this set. So if this set is smooth, then you can use sort of standard PDE techniques like the Hodograph transform or whatever to show that U is as smooth as this free boundary is. So this is one of the other reasons why we care about this functional. There's also this interesting connection where if you care about sort of semi-linear PDEs like this, and you sort of zoom out and look at the large scale behavior of these PDEs, then this large scale behavior is captured in one of 2 different ways. Either the integral of f is equal to 0, in which case the large scale behavior of these PDEs is sort of captured by minimal surfaces. This is sort of the Alen-Kahn equation. Or the integral of this f is equal to 1, or it's non-zero, which you can always sort of normalize to be 1, in which case the large scale behavior of these solutions is kind of captured by the Alt-Caffarelli functional. So somehow the Alt-Caffarelli functional and minimal surfaces have this beautiful connection, and in between them, there's these sort of large-scale behavior of semi-linear PDEs. So if you care about these semi-linear PDEs, it's natural to care about the Alt-Caffarelli functional. This functional is particularly interesting because it's not differentiable. In fact, it's not continuous or convex. And so a lot of sort of the standard techniques that we use to prove regularity are not going to be available for us here. Right? I mean, this part does everything you want it to, but this part doesn't act continuously if U is simply in W12, say. It doesn't even act continuously if U is in C infinity. And this fact that it's not continuous or convex means that it's interesting to distinguish between critical points and minimizers. Contrast this with, say, the obstacle problem, which if you've been following this series of talks, you've seen some talks on. In the obstacle problem, every critical point is a minimizer, but here there are critical points which are not minimizers. And so that makes it sort of interesting to distinguish between variational versus PDE approaches to certain problems. Great, cool. Of course, people are going to jump in if they have questions, right? Fantastic.
Is it interesting to take the measure of the set to a power? Is it regularized?
Oh, yes. So there's a number of different things to think about. So for example, people often look at a similar functional, but you have sort of u to the gamma times the characteristic function of u greater than 0, which is kind of similar to what you're talking about. You could raise this to a power if you'd like, although I've seen that less often. People have also replaced the area with the perimeter, and they're also regularizing things where you sort of try to approximate the area by some f that looks like this, and in an epsilon limit, try to get the area back. So there's sort of a number of different ways of doing it. You can also put a weighting factor in front of the characteristic function. This is sort of the simplest instantiation of one of these problems. Yeah, that's a great question. Thanks.
Okay, thank you.
Anything else? Okay, so let's talk about some basic regularity theory. So Alt and Caffarelli were the first people to sort of really treat this functional in a rigorous way. It had been studied sort of numerically and by physicists before that. And so they proved the following regularity result, which is really beautiful. So for a minimizer, you can partition the free boundary into two sets, a regular part and a singular part. The regular part is beautiful. It's open, it's dense, it has full hn-1 measure inside of the free boundary, and around every point in the regular part, you can write the free boundary as the graph of an analytic function. So what you should be thinking about is, here's your free boundary, here's some point x0, there exists a little ball, so that when you zoom in, there's some plane, and then this set becomes sort of x prime, f of x prime, and this function is analytic, right? So this is the best you can hope for. And if you sort of are familiar with minimal surfaces or the obstacle problem, this should feel kind of good to you, right? These are what regular points do. Unfortunately, there are also these singular points. And at least as far as Alt and Caffarelli were concerned, sort of the only thing they could say about them is that they have 0 hn-1 measure. Sorry, sort of my u lives inside of Rn. So the dimension of the free boundary is n-1. As you can tell, my handwriting is awful, and it's even worse on this tablet. So please excuse it. I'm sorry. Let me know if you can't read anything. Okay, great. Here's some, we've learned more things about the singular points as sort of time has moved on. For example, we know that the singular set is empty when the dimension is less than 4, the ambient dimension. This is a combination of results. Alt and Caffarelli showed it was empty when n is 2, Caffarelli-Jerison-Koenig when n is 3, and then Jerison-Sabin when n is 4. But De Silva and Jerison showed that the singular set is not necessarily empty when n is greater than or equal to 7. They produced minimizers that have singular points. And we'll talk more about those minimizers later. They're quite important. Surprisingly little else is known about the singular set. Weiss, by introducing a monotonicity formula, was able to give dimension bounds in '99. And then more recently, with Nick Edelin, we were able to give some size bounds using the sort of rectifiable Reifenberg / quantitative stratification approach of like Aaron Neighbor and Daniela Vitorta. Let me just talk a little bit about how can you tell if a point is regular. I mean, this decomposition is all well and good, but if you can't distinguish regular points from singular points, then it's a little bit silly. So one thing you can do. Oh, please, yes.
Yeah, so the analyticity of the boundary, do you actually use that level of regularity, or that's just a remark about the scale of regularity? I just wonder whether you can take advantage of the fact that there's an analytic component there. You can embed it into a complex setting.
Yeah, it's a great question. I'm not sure if I've ever seen people really use the analyticity of the boundary. I think analyticity will play an important role in this story in a little bit, which is maybe surprising given that the functional is not analytic. But yeah, I think, so in general, people look at things like q plus of x times the characteristic function of u. And then the point is that the free boundary is as regular as q is. And here I've set q to be identically equal to 1. So the free boundary is analytic. Does that answer your question? Maybe not quite.
Yeah, no, again, it's just the extent to which you use in the subsequent analysis the strength of it being analytic versus just simply being C infinity or sufficiently smooth.
We're going to use like C2 alpha.
That's what I mean. So I just wonder whether there may be some other dimensions that one can explore, knowing that it's analytic.
It's certainly possible. There are some complex analytic approaches to this problem in 2 dimensions, which may be, it's then useful to know some analyticity.
Yeah,
I'm really
just curious.
Yeah, absolutely. So back to this question of how does one tell a point is regular? So what you do is you look at your free boundary, and then if at any point and at a scale, if you zoom in at that point in scale, if you can trap the free boundary between 2 planes, which are sort of, let's say, close to one another, and closeness depends on the ambient dimension, then this point is regular. But if your free boundary looks something like this, then at this point, you can never trap the free boundary between 2 planes that are close together, right? No matter how much you zoom in. And these points are going to be singular. And immediately from this characterization, you can see why being a regular point is an open condition, right? Because if you can trap the free boundary around this point between 2 planes, then you can trap the free boundary around this point between 2 planes by just zooming in a little bit more and maybe rotating the planes a bit. Okay, so this is sort of standard free boundary regularity. And we'll be talking for most of the day about the singular set. Great. So the thing that you really want to do in almost all of these problems is what's called a blow-up procedure. Alt-Caffarelli told us that, well, another consequence of the work of Alt-Caffarelli is that a minimizer is always proportional to the distance from the point to the free boundary, which is sort of telling you that this Lipschitz scaling is the correct scaling for the problem. And then you can use some sort of standard compactness results to show that if you take a limit of scales as rj goes to 0, in the limit you'll get a minimizer, this u infinity. It's going to be globally defined because you're sort of zooming in, and so the domain of definition will be the entire Rn, and it's going to be non-trivial because this condition tells you in the limit that u infinity isn't identically equal to 0, and it's not identically equal to infinity, right? So that's why you chose this scaling. And sort of, you could think of this scaling both in terms of the function, but also geometrically, right? So here you have some free boundary, we pick a point, we pick a scale, rj, and then this becomes, right? So this point was x0, and this now becomes 0, and at scale 1. And the idea is somehow that the singular set of u near x0 should be sort of approximated by the singular set of u infinity near 0, right? So if you had some free boundary, which maybe had a lot of singular points, who knows, then when you zoom in, you should somehow see all these singularities in the limit. And this is why it's useful to study the blow-up if you want to understand the singular points. Okay, so how are we going to understand these blow-ups? The sort of key tool always is something which is called a monotonicity formula. So Weiss in '99 sort of observed that if you take the energy, scale it appropriately, and subtract off a sort of boundary term, then this function is a monotone increasing function in R, as long as u is a minimizer and x0 is in the free boundary. It actually works for critical points also. And actually, he proves something a little bit more. He shows that the derivative is bounded from below by how far u is from being one homogeneous. Note that this is equal to 0 if and only if u is one homogeneous. Okay, so now we're going to do a little proof, essentially, that blowups are always one homogeneous functions. We notice that because of monotonicity, this limit at 0 exists, and this monotone function really does well under scaling, right? Remember that ux r0 is u of rx plus x0 over r. So if these rj's go to u infinity, then this tells you that the monotone quantity applied to u infinity is independent of the scale. Or in other words, that ddr of w u infinity 0 lambda is identically equal to 0. But then you can see from this term that that means that u infinity has to be one homogeneous. And indeed. Okay, so this is great. We have zoomed in at these singular points. We get a one homogeneous function. And now we're going to try to understand the singularities of the original function by understanding the singularities of one homogeneous functions. And what's really nice about the singularities of one homogeneous functions is that they all live inside of affine spaces, right? If your cone has a singular point, then it either has to be isolated, or it has a line of singularities, or it has a plane of singularities, but it can't have a wavy set of singularities. That's not how one homogeneous functions work. And just as a little sort of check, our favorite one homogeneous function is xn plus. And indeed, this is the blowup you get if you do this procedure at a regular point. So that's great. Okay, but I mentioned before that there are examples of non-flat, or sorry, of free boundaries with singular points. And that means that there have to be examples of cones which are not xn plus, right? There have to be examples of one homogeneous minimizers which are not xn plus. And these examples are called the de Silva-Jerison cones because they were discovered by Daniela de Silva and David Jerison in their 2009 paper. Okay, and so what do we know about them? We know that they're one homogeneous. So I'm going to split up the function in polar coordinates, right? Theta lives in Sn minus 1. And we can just do some sort of basic analysis. If u is positive and harmonic, then you can write the Laplacian in polar coordinates, and you can see that this phi above has to be the first Dirichlet eigenvalue, or eigenfunction, I'm sorry, of the positivity of set of u in the sphere. And that the eigenvalue of that set has to be equal to n minus 1. So this is just the separation of variables argument. And you know it has to be the first Dirichlet eigenvalue because of positivity, right? It doesn't change sign. Okay, so let's think about some very simple domains on the sphere where we could try to see if they satisfy this condition. Well, the simplest domain on a sphere is a spherical cap. And this will satisfy the condition that the first Dirichlet eigenvalue is equal to n minus 1 if it's the equator, which is nice because this corresponds to xn plus. So the next simplest thing you could try is this cone. So what does this cone look like? Here's your sphere. Oh, wow, this is the best sphere I've ever drawn. Everyone's in luck today. And the positivity area is the stuff between the circles. And how far these circles are depends on the t here, right? So the t sort of tells you how squished your cone is. And it's a simple calculation to show that there's exactly one sort of squishiness factor, which gives you that lambda 1 of this cone is equal to n minus 1. And then the hard work of de Silva-Jerison was to show that in dimensions greater than 7, this is actually a minimizing cone. Because note, this cone exists in every dimension greater than or equal to 3. But it was shown in earlier work not to be minimizing for the lower dimensions. So there's something weird that goes on here. Although perhaps if you're familiar with minimal surfaces, this is not so surprising, right? These sort of Simons type cones where you have R2n, and then you look at x equals y instead of R2n, where x is Rn and y is in Rn. These cones exist in low dimension, but they're only minimizing when 2n is equal to 8 or above. So this is a very similar phenomenon. And these are the only known examples of one-homogeneous minimizers which are not xn plus. But I put this in square quotes because it's not quite true. Each of these cones has an isolated singularity at the origin. But of course, what you could do is you could take the cone from n equals 7 and put it inside n equals 8 by just taking the same cone and crossing it with a linear factor, right? So now there's a bunch of singularities, a line of singularities. So actually, there's a family of de Silva-Jerison cones, right? There's one with an isolated singularity for every dimension, and then for any dimension 7 plus k, there's one with a k-dimensional space of singularities, which is take the 7-dimensional cone and cross it with an rk factor. Okay, so hopefully this makes some sense. Let's sort of move on from here. So what's the end goal of this whole project? We have a minimizer, we have a singular point in the free boundary, and we have this blow up procedure, right? So we've found some r sub j which go down to 0, and u of rjx plus x0 over rj converges to this u infinity. What we hope is that two things are true. One, that this u infinity is unique, that it doesn't matter what scales we zoom in on, we always get the same cone in the limit. And then, if we're being very ambitious, and why not, it's a conjecture, we can hope there's a smooth bijection in the ambient space. And what it does is it takes your original free boundary and it writes it as the map of the free boundary of your limit, right? So this is u infinity greater than 0. So you have some ambient map here for the free boundary of the limit, and you can parameterize locally the free boundary of your original function by the free boundary of your limit. This would be the ideal thing. And note that this is exactly the theorem of Alt-Caffarelli for flat points. We're saying that you have some free boundary here, and you can write it as a very beautiful graph over a flat set, right? That's what it means to be a graph. There are analogs of these conjectures for minimal surfaces, obstacle problems, any number of problems in the calculus of variations. Note that you can't hope to have the more ambitious parameterization result without first having the uniqueness result. This is just sort of a fact. And whenever I give this talk to people who don't sort of work in the calculus of variations, they might think, okay, I get it, you're using compactness here, but there's no way that you can have non-unique blowups. But actually, there's a really beautiful construction of Brian White in the early 80s, which shows that if you have a harmonic map into a C infinity target, not an analytic target, then you can construct a harmonic map, which is minimizing. So remember, harmonic maps minimize the Dirichlet energy, but subject to the constraint that U goes from, say, a manifold M to a manifold N, right? So this is a non-convex constraint. You can have a harmonic map which has a singular point at the origin and has a continuum of different blowups at that singular point. So you get different blowups, you get different U infinities depending on the scales that you zoom in on. It's like a fractal-like structure almost, right? Okay, so this is a really serious issue. I mean, uniqueness of blowups can fail in certain situations. And why should you care about such a parameterized such a conjecture? Well, the idea is that if you care about these free boundary problems because they model physical phenomenon, then this parameterization is a type of stability almost, right? It's telling you that infinitesimally, you really do understand what's going on, and that you can't have sort of different infinitesimal behaviors as you zoom in at different scales, which feels very non-physical. And also, if you care about these applications, if you care about these free boundary problems or minimal surfaces because they show up in geometry, then these parameterizations are quite useful for applications. So for example, people often care about foliations of minimal surfaces. And the idea is that you foliate your domain by minimal surfaces, and then you should be able to get local geometric information. But this is less helpful if the minimal surfaces have singularities, unless you have a parameterization of this type around those singularities. And then you can still get quite a bit of geometric information. So these types of conjectures really do have serious consequences in other branches of mathematics. Right.
So just a question if I could. So again, the types of singularities that you're trying to avoid are concentrations of curvature?
Interesting. So oftentimes in other problems, you can write these as exactly concentrations of curvature, right? For things like minimal surfaces, I think, and certainly for things like, you know, manifolds with bounded Ricci curvature. Certainly the curvature concentrates here. I find that perspective to be less helpful because you don't see the curvature explicitly in the functional, right? So it's not so easy to identify where the curvature would concentrate. Like the connection between curvature concentration and the energy is not so clear to me. But certainly, yes, the types of singularities that you're looking at are all going to be conical, at least infinitesimally.
Okay, thank you.
Of course. Anything else? Okay. So I guess it's about time that I give you a theorem, right? You've been waiting for about 30 minutes. So here's a theorem joint with Luca and Bojo. It just came out in the journal this year, which we're very happy about. So it says you have a minimizer to your functional and you have a singular point. And imagine that you have one blowup with an isolated singularity, right? So what are we thinking about? We're thinking about something that looks like this, not something that looks like this, right? Where you have a whole line of singularities. This is bad. Then this is the unique blowup. Note that it's possible that you could have zoomed in at some scales and seen this one, and zoomed in at other scales and seen the non-unique blowup. Or even you could have zoomed in and seen this cone at some scales, but seen a rotated version of this cone at other scales. And this theorem is telling you no. If you see this cone along one set of scales, that's the only cone you're going to see along any set of scales at that point. And actually, we can tell you a little bit more. We can tell you that there's a scale at which you can write the original free boundary as a graph over the free boundary of the blowup, right? So that's what this thing in red is telling me. I'll tell you a lot more about this C1 log here, but really you should think of it as C1 plus control of the modulus of continuity. And actually, if your blowup satisfies an extra structural condition, which we're going to call integrability, and we'll talk about that more later, then the C1 log regularity can be upgraded to C1 alpha. And what's really nice is we do a computation to show that these de Silva-Jerison cones, the only examples of minimizing cones we know, actually satisfy this extra structure condition. So we really do get C1 alpha regularity at these cones. Okay. I've already sort of talked to you about the isolated singularity versus non-isolated singularity. As we go through the proof, we'll see why that distinction is incredibly important. Yeah, so what do I mean by a C1 log graph over the cone? Really what I mean is take your cone, cut it off around the origin. Then you can write your free boundary as sort of a graph along this cone like that. I don't know if my picture is really doing it justice. Right, I mean, asking for something to be a graph over a singular object doesn't really make a lot of sense. So we cut off the cone around the origin, we say it's a graph along that, and then the point is that the norms of the graph don't depend on the neighborhood that we cut out, right? So we have sort of uniformity as we go towards the origin. Hopefully that makes some sense. The C1 log versus C1 alpha issue. So you might ask, Max, I don't understand. How do you get C1 log when you say you have C1 alpha for the only cones that you know actually exist, these de Silva-Jerison cones? But maybe let me say that there are examples in the obstacle problem and in minimal surfaces which tell you that you can't always get C1 alpha regularity around isolated singularities. We don't know that these examples also exist in the Alt-Caffarelli functional, but we sort of have reason to suspect that they might. And that's why the C1 log theorem also carries some information. And we'll talk more about that distinction later. Maybe I'll skip this discussion of parameterization because I think I'm running a little bit behind. Okay, so what's my key tool here? My key tool is something called an epiperimetric inequality, which is a little bit complicated, so let's go through it slowly. You take your one homogeneous critical point, and you let C be any function in L2 of the sphere. Then there exist these two parameters, epsilon naught or epsilon tilde and delta, such that if C is close to B inside the sphere, then you can find an extension of C into the ball such that, remember, this is these Weiss energies. The Weiss energy of the extension is strictly less than the Weiss energy of R times C, right? So by that, we mean the function which is given by R times C theta in spherical coordinates. So this is the one homogeneous extension. One homogeneous. So let me point out that if this epsilon, if this is equal to 0, then the epiperimetric inequality has 0 content. Because if you just let H be a minimizer with trace C, then of course the energy of H will be less than the energy of RC. That's the definition of being a minimizer. So the content of this theorem is that it's not that the left-hand side is less than the right-hand side. It's that there's always a gap in the energy. This epsilon tilde is doing all the work for you. Okay, so exactly what I was saying before, minimizers are quantitatively smaller than one homogeneous competitors. How much smaller? Proportional to how far away C is from being B, essentially. And what do I mean by delta close? Well, I probably mean something like C minus B in L2 is less than delta, but I also mean that if this is the free boundary of B inside the sphere, I want the free boundary of C to be written as the graph of a function. So I want the graph over partial B greater than 0 of zeta to be equal to the free boundary of C. And I want zeta to have small C2 alpha norm. This is a technical condition, but it's incredibly important, and we'll come back to it later. So we need two types of closeness. This is what we mean by delta closeness. And who is this epsilon tilde? This epsilon tilde is an absolute constant epsilon, which depends only on B, times the difference in energy on the right-hand side to the gamma. And gamma is going to be a constant, again, which depends only on B, which is between 0 and 1. And this integrability condition that I was talking about before, this extra special symmetry, which gives me a better rate of convergence, this integrability condition is going to be exactly the condition when I can take gamma equal to 0. And we'll talk more about that later. Okay, so right now there's a lot of constants floating around. It's all very mysterious, but I hope to explain it better. So let me just say very briefly, and at the end, if there are questions, I can give more details, why epiperimetric gives you uniqueness. Through a very slick arithmetic argument, the epiperimetric inequality gives you an upper bound on the derivative of this Weiss monotonicity. And here is the only place where you use that U has to be a minimizer. This is very important. And then Weiss observed that an upper bound on the derivative of W gives a rate of convergence. And you can see that, right? Because remember in a previous slide, ddr of ur was greater than or equal to 1 over r to the n plus 3 times this thing, which measured how far away we were from being one homogeneous. So if this goes to 0 fast, this has to go to 0 fast, and that means that we have to approach our one homogeneous thing at a rate. And that rate of convergence will give you uniqueness and the parameterization. Okay, so let me stop here. Are there any questions about epiperimetric?
Okay, thank you very much.
Oh, no, sorry. No, I'm not done. I just wanted to ask if there were any questions about this theorem. You have to listen to me for a little bit longer yet. I'm sorry. Okay, but it doesn't seem like there are any questions. So maybe I'll sort of move to, I'll tell you a little bit about the history of epiperimetric, and then I'll tell you a little bit about the proof. I think I still have about 10 to 15 minutes. Okay, great. So a history of epiperimetric inequalities. They were actually first introduced by Reifenberg in 1964 to prove regularity for area minimizers. This is around the same time as de Giorgi's scheme for regularity of energy minimizers came out. I would say that the de Giorgi scheme was a lot more long-lasting than Reifenberg's. Part of this is because it had implications in a lot of things in the calculus of variations, but also part of this is because Reifenberg died very shortly after proving this theorem in a mountain climbing accident. There's been other results using epiperimetric for area minimizers. Taylor used it to prove, she used it to prove uniqueness of soap films at every point. So these are things that look like sort of these types of singularities, or there are tetrahedral singularities as well. Brian White later used it to prove the uniqueness almost everywhere of the blowup for two-dimensional, almost area minimizing currents. So this allows for multiplicity in particular. And then as a companion paper to the one that I'm talking about today, with Luca and Bojo, we used it to prove uniqueness of isolated singularities for almost area minimizers in any dimension, but the singularity has to be isolated, and multiplicity 1 is an important thing as well. These are technical things in area minimizers. There's also been a lot of work for free boundary problems. Weiss, in a different paper in '99 than the one I've been citing before, first introduced it to show uniqueness at regular points and some singular points for the obstacle problem. And then there have been work for the thin obstacle problem by Garofalo, Petrosian, and Smith-Vega-Garcia, and Riccardi Spadaro. And then more recently, Luca and Bojo, and then Luca and Bojo with Maria, proved uniqueness at all points for both the thin and classical obstacle problems. And then even more recently, there's been some work for the parabolic thin obstacle problem. But what's this blue versus red on the slide that you see? It's a distinction which is very important in epiperimetric inequalities, which is by contradiction versus direct proof. So one thing you could try to do is prove an epiperimetric inequality by contradiction. But if you do this, you'll often only be able to prove the epiperimetric inequality around very particular types of blowups. So usually regular points and maybe some very constrained types of singular points. Direct proofs, where you actually produce the competitor H that we talked about on the previous slide, allow you to have a lot more flexibility with the types of blowups that you're able to address. And our proof here is direct. This is sort of one thing that I'd like to emphasize, is that it's a new approach to proving epiperimetric inequalities, one that doesn't work by contradiction, but where you actually build the H by hand. I'd also really like to highlight these two works by Maria, Luca, and Bojo. They introduced this idea of the logarithmic epiperimetric inequality. So everyone else had only done the case when gamma equals 0 on the previous page. And they realized that when gamma is not equal to 0, you can actually still learn something about the singular points. So this is a huge breakthrough. It was really, really nice idea. Great. So maybe let me talk a little bit about the proof in the remaining 10 minutes or so. So what makes the Alt-Caffarelli function hard? There are two terms, right? The Dirichlet energy and the area. And these terms are very balanced when U is close to being one homogeneous, right? If one of the terms dominated the other, then it wouldn't be that difficult. It would either be a harmonic function or it would be an area minimizer. But because the two terms are balanced, you really have to deal with them both at the same time. But they're only balanced when U is close to one homogeneous. So what you can do is you can write your function C. Remember, we start with a C in L2 of B1, or partial B1. You can write it as a sum of the Dirichlet eigenfunctions of the Laplacian on its positivity set. And if it projects in a large way on any of the higher modes, then that means that C isn't close to being one homogeneous. It's only this first mode where you can see one homogeneity. Well, it's only phi1. And so if any of these other projections are large, we can just extend C to be harmonic, and we'll get the epiperimetric inequality without any hard work. And this is an observation of Luca and Bojo in a previous paper. So what's really difficult is when we start off with a function C, which is close to being, whose one homogeneous extension is close to being its harmonic extension, if you'd like. So that's what we're going to do. We're going to start off with function C. And in that case, the epiperimetric inequality reduces down to understanding a different functional. You take the first Dirichlet eigenfunction of the positivity set of C and subtract off the first Dirichlet eigenfunction of the positivity set of B. Remember that this number is n minus 1 because B is a one homogeneous minimizer. And then you take the area of the positivity set of C and subtract off the area of the positivity set of B inside the ball. So now you really just need to understand how the first Dirichlet eigenfunction versus the area talk to one another inside of the sphere. So what's the idea? To create our competitor H, we're going to change the positivity set of C slice by slice inside the ball, trying to decrease this functional as quickly as we can. So we want a sort of gradient flow of this functional, if that makes sense. Cool. So here's our functional. I've written it down again in red. And I've made this notational choice, which I call omega sub zeta. And this is exactly what I was talking about before, right? Where if this is the positivity set of B, I'm asking that omega sub zeta is given sort of as the graph over this thing by the function. Oh man, just forgot how to draw zeta for a second. By the function zeta, right? So we're only looking at the graphical perturbation sense. And this is an abuse of notation, obviously, but you sort of know what I mean by this. Okay, so let's notice a couple things. First, this function at 0 is equal to 0, because when zeta equals 0, omega sub 0 is exactly equal to the positivity set of B, and then its first Dirichlet eigenvalue is n minus 1, and its area is exactly the area of the positivity set of B. And because B is a critical point, this means that the derivative of f at 0 is also equal to 0. So if we take a Taylor series, we really want to understand the second derivative of f at 0 in the direction zeta. That's the thing that we're trying to figure out here. And now you do a little bit of functional analysis. You can really do a computation. You can show that this second derivative is a symmetric bilinear form. It's bounded from below. And that means that you can diagonalize it, right, using sort of spectral decomposition. And you can write your zeta as an orthogonal sum, a zeta plus, a zeta 0, and a zeta minus. And this functional changes in a quantitative way in the directions of zeta plus and minus, right? They're in the sort of positive and negative eigenspaces. But it doesn't change at all to second order in the 0 directions. So if I want to shrink this functional as I'm building my competitor inside the ball, well, the recipe is easy. I should be sort of pulling down on the zeta plus directions and leaving the zeta minus directions alone, right? Or even pushing up on them. But of course, the difficult thing is what happens if basically my entire graph is in the zeta 0 direction, right? If the whole thing is in the kernel, then I don't really understand what's happening as I perturb things. At least I don't understand what's happening to second order. Okay, so now let's talk about the kernel. The things in this kernel, as I said before, are exactly the perturbations that don't change our energy to second order. And the big idea is this concept of integrability, which was first introduced by Allard and Almgren for minimal surfaces. I don't know why I flipped their names alphabetically. So U is an integrable critical point of M if all the deformations of U, which keep M the same to second order, is generated by a family of critical points. And let me try to give you some examples, right? So we know the concept of being a more spot critical point, right? So now imagine that F is just a function from Rn to R, x0 is more spot if the Hessian of F at x0 is, is non-singular. And this is basically telling you that no matter what directions you move away from x0, you always change F to second order. But there's another possibility. It's possible that you have something like this, F of x, y, z, which is simply equal to x squared plus y squared. Well, this F isn't more spot, right? If you move in the z direction, you're not changing F to second order. But on the other hand, if you move away from the origin in the z direction, you really just hit other critical points, right? F doesn't depend on z at all. So 0 is a critical point, but so is 0, 0, 1. And this is sort of corresponds to the integrable case. But of course, you could also have directions where F changes, it just doesn't change to second order. So something like this, F of xy equals x to the third plus y squared. If you change the x coordinate, F certainly changes, but still the second derivative of F in the x direction is singular, right? It is equal to 0. So this corresponds to the non-integrable case. Right, so here's sort of, obviously these are questions about functionals, so they're infinite dimensional things, but this is the idea in finite dimensions. So in our paper, we introduce an analog of integrability for the Alt-Caffarelli functional. This is a little bit complicated. In the integrable setting, let me skip over this kind of quickly. It's easy to get rid of the kernel. Basically, if you have kernel, if you have zeta 0, it means that you parameterized over the wrong critical point. You should have started your whole argument over B prime instead of B, where B prime is a critical point which sort of generates the kernel direction zeta 0. So this is easy in the integrable or not easy, but it's a lot simpler in the integrable case. You don't need to care about the kernel. If you have non-integrable kernel, then you can perturb in the kernel direction and still change the area, right? This is the F equals x to the third plus y squared case. So how do we modify the elements in the kernel to decrease F? Well, you want to take a gradient flow. But remember, the epiperimetric inequality is all about quantitative improvement. So how do we know that our gradient flow quantitatively improves? Here, we use something which is called a Wojciewicz inequality. And the Wojciewicz inequality tells you that gradient flows of analytic functions quantitatively decrease energy. But Wojciewicz inequalities are only for finite dimensional analytic functions. And here, functional analysis saves us again, because we know that the dimension of our kernel is finite dimensional from spectral theory. So essentially, this tells us that we can apply the Wojciewicz inequality, being quite careful, to the elements of the kernel. So maybe in my last minute or two, let me just tell you a little bit about the Wojciewicz inequality, because it's kind of cool. The Wojciewicz inequality says that near a critical point, an analytic function grows at a certain rate, and that rate is captured by this exponent gamma. And this exponent gamma is exactly the exponent gamma that we get in our epiperimetric inequality, maybe like divided by 2 or subtracted 1 or something like this. And as a corollary, it tells us exactly what we were talking about in the previous slide. Gradient flows of analytic functions decrease energy at a quantitative rate. And this quantitative rate is given by gamma. So you should think of this gamma as measuring how far along in the Taylor series expansion around x0 you have to go before you get a non-zero term. If the Hessian is non-zero, then gamma is equal to 2. But if you have to go all the way to the kth term, then gamma is equal to something like k over k minus 1, or something like that. Wojciechowicz was a real algebraic geometer. He didn't care about analysis, really. He was doing this to understand analytic varieties. But it was Leon Simon later in the 20th century who realized that you could use this functional to understand the gradient flows of elliptic functionals. You could use this theorem. So these Simon-Wojciechowicz inequalities have been used all over geometric analysis to understand the uniqueness of blowups or long-term behaviors of flows in elliptic and parabolic problems. Mean curvature flow, the Yamabe problem, minimal surfaces, all over the place. But I think what's interesting about our particular application is that usually they're used for something that is a critical point that satisfies an equation. And we can't do that because our equations that we're looking at aren't sort of generated by analytic functionals. So we use it to prove a quantitative inequality via a gradient flow. And that I think is a relatively new idea, which we sort of liked. So that's maybe a take we have.
Sorry, Matt, you have 2 minutes.
Perfect, because this is my last slide. So maybe I'll leave up some lessons and drawbacks. And if you have any questions, I'd be happy to answer them. Thank you very much for your attention.